In this lesson, we want to review some key features of polynomials and look at ways to multiply them based on what you've already know. So the first part of this lesson will be a review of multiplying a monomial times other types of terms, and then in the second part of this lesson we'll get into some new stuff that you haven't learned before. So before we begin, we have to ask ourselves, in mathematics, what do we mean when we say the word term? So terms actually consist of 4 different parts, and I'm going to use the example of negative 4x to the 5th. I can take this part and I can divide it into the first 2 pieces right here, which are called the numerical coefficient. And the numerical coefficient consists of 2 sub-pieces as well. It consists of a sign, which if it's absent is assumed to be positive. If it's there, of course, written like this, it's negative. The plus can appear there as well. And then it also is broken into a value. And here we can see the value is an integer value. It's negative 4, but it doesn't have to be. It can be a decimal, it can be a fraction, it can be any type of value belonging to any number system that we wish. So then there's a second half to this term right here, and this is called the literal coefficient because it's based on having letters in it. Sometimes we nickname this the variable. Now you'll notice that it consists of 2 pieces as well. It consists of a letter and it consists of an exponent. Okay, because it has both a base and an exponent, this entire thing is also referred to as a power. Okay, so when we talk about terms, we have to be mindful of all 4 parts: sign, value, letter, exponent. Sign, value, letter, exponent. And when we look at operations involving terms, we also have to be mindful of all 4 of these parts and how they interact with each other. So we can say that terms are alike if they have the same literal coefficient. So if I have 2x to the 5ths and I have another 7x to the 5ths, altogether I have what would be called 9x to the 5ths because the literal component of these terms is identical. And it's kind of like the analogy of saying I have 2 apples and 7 apples, and that would give me 9 apples. So 2 things, 7 things, 9 things. The thing is the literal coefficient. So let's quickly review then what we've just learned. So if I give you the term negative a to the 10th, can you tell me what the numerical coefficient would be and what the literal coefficient would be? Well, the numerical coefficient consists of both the sign and the value. If there's no value here, we assume that value to be a 1. The literal coefficient is the letter with its exponent, or this power, so it would be a to the 10th. If I give you a term of 9b, the numerical piece again consists of a sign and a letter. So there is no sign shown, which means that it's positive. We understand it to be as such, and the value here is 9. The literal coefficient, or the variable, is the power piece. So here it just says b, and if no exponent is shown, just like there was no sign here or no value here, in this scenario the exponent is assumed to be a 1. So I want to be explicit in showing that here. Finally, if I give you 47c to the 4th, d to the 5th, this looks a little bit different from some of the other terms we've done because it has 2 power pieces. Nonetheless, just because it has 2 power pieces means that this entire thing is the literal coefficient. So I'm going to do this one a little bit backwards. I'm going to say the literal coefficient is c to the 4th, d to the 5th. And the numerical coefficient, again, no sign, so it's assumed to be positive, and a value of 47. And terms are always written in this order, with the numerical coefficient first and the literal coefficient second for clarification, so there's never any discrepancies between them. All right, now I want to also review some subsets of the word polynomial. Poly just means many, and nomial just means many terms. So if we have something called a monomial, it means we only have one term, because the word mono means one. So if we could include some examples of monomials, you can create your own numerical coefficient piece combined together with your own literal coefficient piece. So why don't we, for the sake of an example, use G for Gerber, and we'll put it to the 48th for no particular reason. And for the numerical coefficient, let's make it negative, and since we'll do something like a 10 here. Okay, so negative 10g to the 48th. And there would be no space. We would put these side by side. I just wanted to clarify the different parts of that term. A binomial means that there is a collection of two terms. So in order for us to have a collection of two terms, we have to make sure that their literal coefficients are different. If they're the same, then it would not be considered a binomial because they can be simplified into a single monomial. So let's include a negative example and a positive example. Let's maybe do negative 7ab squared, and then plus 4cb squared. And you might say, well, aren't those the same? Well, the b squared parts are the same, but in order for them to be like terms, these literal parts have to perfectly match. And since they don't perfectly match, that's not the same. Okay? A trinomial would be three terms. And so as long as the literal parts in all three terms are different, that's okay. So we could do something like 2xy plus 2yz plus 2xz if we wanted to. And even though the numerical parts are the same, the literal parts are different, so these are different terms. And a polynomial would just be a collection of more than, let's say, three terms for the sake of creating some definitions for you in your note. Okay, so what I want to finish up with in this particular lesson is I want to remind us how to multiply terms together. Because adding and subtracting them, we've actually kind of already done. You can only add and subtract terms if they are like. If they're not like, you can't do it because they're not the same type of term. So let's go into some examples of using the distributive property where we take a monomial and multiply it by a polynomial. So the first example in your notes is 3 times the quantity 4x minus 6. And so here we see the monomial. Okay, it's just a term all by itself. It doesn't have a literal part, so we call this a constant because its value is always going to remain the same. And then here we have a collection of two terms, 4x and negative 6. So this is a binomial times a monomial. Now, when we multiply terms together, it's super important that we recognize those four parts of a term. And you'll remember that they are sign, which is either plus or minus, a value, a letter, and an exponent. Okay? And we have to make sure that we account for all four of those as we multiply. So when I do the distributive property, what I really recognize is that there are 3 4x minus 6's. And therefore, because there's 3 of them, there have to be 3 4x's and 3 minus 6's. So I can expand that all out if I want to, or I can recognize that I can just take this 3 and multiply it by each of the terms inside the brackets. So when I multiply these two together, and I'll highlight them for you, I want to make sure that I collect the sign, the value, the letter, and the exponent for here, and I also want to do it for here as well. So the two signs multiplied together are positive. If I don't write a sign, I'll know what it is. If I multiply their values together, I get 12. Letter and exponent, there are no letters or exponents in this term, so we would just leave this as an x. And then if I do the same thing with multiplying 3 times negative 6, again, positive times negative becomes negative, and the values 3 times 6 becomes 18, and there are no letters or exponents to worry about in these terms because they're both constant values, and so then we're finished. Okay, let's up the ante a little bit more. Let's take a monomial where we can clearly see 3 of the 4 parts. Let's do negative 5x. The fourth part, the exponent, is not shown, therefore it is a 1, but it's still there. And let's multiply it this time by a trinomial. And again, it's a trinomial because each of these terms have different literal parts. This one's x squared, this is x to the first, and this one doesn't have one. So when we use the distributive property, we want to make sure that we multiply sign times value times letter times exponent for each of those terms, making sure to leave nothing out. So, in the first case, I have negative times positive, which is negative, 5 times 1, which is 5, and then x times x, or x to the first times x squared. So x to the first times x squared means x times x times x. Okay, because exponents are just ways of showing repeated multiplication. So how many times does x get multiplied by itself? Well, it gets multiplied by itself 3 times. That's not the same as 3 times x. It just means x times x times x. So I can write this as x cubed. I should do it in orange just to keep consistent with the color pattern here. All right, so that's done. Let's look at negative 5 times positive x. Signs first. Negative times positive is negative, 5 times 1 is 5, and x times x is x squared, or x times itself, so that there are 2 of them. Lastly, signs get multiplied. Negative times negative is positive, 5 times 7 is 35, and there's no literal part here, so we're still multiplying all those through just by x. All right, let's do one final example for this lesson, and then we'll switch to page 2 of your note in the next video. 2x times y squared minus y plus 8, all in brackets, minus 3y times 2x squared plus 6x minus 9. Okay, again, you want to be careful that the monomial that's in front and all 4 of its parts get multiplied by all 4 parts of the terms inside the brackets. Okay, what I find useful is to highlight that monomial out in front so that I'm cognizant of all 4 of those parts. I'm going to do the same thing here as well. And then I make sure not to leave anything behind inside either. Sign, value, letter, exponent, sign, value, letter, exponent, sign, letter, variable, sign, value, letter, exponent. There we go. All right, so see, I've made sure that nothing gets forgotten about. Okay? And I'm going to add these in so that you can see that I'm multiplying that monomial by each of the terms inside the trinomials that follow. All right. Signs. Positive. 2 times 1. 2. X times y squared. Xy squared. Next one. Positive 2 times negative 1. We can maybe lump those 2 together now to save a bit of time. Negative 2. X times y is just x times y. Positive 2 times positive 8, 16. No literal part here, so just x from this term here. Done all of those, let's move to the next one. Signs. Negative 3 times positive 2, and value together would be negative 6. X squared times y, or y times x squared. We can write it that way, but generally it's nice to do these alphabetically because when you're multiplying, it doesn't matter what order they go in, because we're going to collect like terms eventually in this very expanded example anyway. So I'm going to write it like this instead with the x ahead of the y. Negative 3 times positive 6, negative 18. X times y, again I'll write it alphabetically. And then finally, negative 3 times negative 9 would be positive 27, and the only literal part that's left is here. Now, we've done the distribution, but we need to simplify this because there are some like terms in here. Can you see them? The ones that have the same literal part. Well, if I start at the left side, I see x times y squared here, but I don't see any other x times y squareds at all. So I'm going to rewrite that one as is. And I'm just going to do this so that I know I've dealt with it. Next, I see a type of term that is x times y. Are there any others? Yes. So let's identify those terms that are like using sign, value, letter, and exponent. Sign, value, letter, and exponent. So if I have negative 2 things and negative 18 things, altogether I have negative 20 of those things. And in this case, those things are x, y's. Okay? I'm just going to do this so I know that I'm done. Now, let's look at, see if there are any other types. This is an x-type term. There are no other x-type terms, so I'm just going to leave it as is. Here is an x squared y term. Again, no other term like it, so I can leave it as is. And here is a y-type term. It's the only one, so therefore this answer is as simplified as it can be. So there's a quick review of what a term is, the parts of a term. The other thing I want to let you go with before I stop the lesson is I want to talk about degree of a polynomial. Now, degree of a polynomial is simply its highest or its greatest exponent value. So if I have something that has, say, an x cubed term in it and maybe an x squared y, well, in fact, let's just go to the example of above here, okay? This particular term here has x to the first and y to the second. This one has just x to the first, this is x to the first, y to the first, and so on. All combined, if you look at all the exponents in here, you have a total of 1 plus 2 is 3, or power, highest degree of 3. 2 plus 1 here is also 3. These two are the highest polynomials. Generally, when we talk about degree of a polynomial, we don't talk about it when there are mixed literal coefficients or more than one letter present. So let me be more specific. If I have, say, 2x cubed plus 4x squared minus 10x minus 21, and if I look just at the literal parts, this one doesn't have one. This is x to the first, this is x to the second, this is x to the third. This one has the highest exponent, and so therefore we would say that this is a third degree polynomial. Okay? All right. I'll meet you in the next lesson for the second half of your handout.